Okay, so off camera, I found the DR positions for the other two problems that we're going to be working off of. So you can see here we have the 4th of June. I set up our plotting sheet. We're working generally in the area of 27 degrees south and 122 degrees west. Here was our DR position as we list out the original DR position as we list out in the problem. And then here's the DR position at the time of the shot. And if I pull out my notebook, I really got to start saving the pages. Damn it. Here we go. 4th of June. This DR position, this 9:15 one, I measured as having a position of 26 degrees 30 minutes south, 21 degrees 56 minutes west. And then for the next problem, set up the same thing. The one difference between these two is I wanted to show you the different ways you could set up a plotting sheet. So if you're in the south, realistically everything is upside down. For this one, what I did was I kept the paper oriented the normal way, meaning that these numbers go up this way, which is technically wrong. So you kind of have to flip them in your head to measure downwards in this direction. But then as a result, you can still kind of read everything normally. For this problem, which is taking place 23 degrees south, I actually flipped the entire paper upside down. So now the words are upside down, but you can still kind of measure it the normal way. Just to show you the two different ways you can work with these plotting sheets. And then I got the DR position for the time of the shot for this one as well. So now that we have these DR positions, we can actually begin with the with doing the math part of cell nav. So we've got the three problems, and we're just going to start with this one and work exclusively on the first portions of the problem. So, actually, our DR position isn't going to matter yet anyway, even though we just put in all that effort. The very first thing you need to do in a DR position is you need to find your GMT time. You'll see why. It's because the Nautical Almanac is written all in GMT, so we need to get ourselves there first. So the first things you write are ZT, then CT, then CE, and then GMT. And this is going to be true for all three of the problems. Some people write this slightly differently, like they combine CE and ZD, or they don't combine it or whatever. But you'll see what I'm doing in a second. Now ZT. This is just the time of our shot, which was at 10:36. Now chronometer time, you can see that I kind of glazed over this, but it was written here before. The chronometer is just the physical clock on your bridge. And a chronometer is always in GMT. The official chronometer for your ship is kept in GMT. And frustratingly, it's also only in 12-hour time. It's a normal like a normal analog clock. It's just got a 12 hands on the clock. So you have to know whether you're working in AM and PM. So whenever you have a chronometer time like here, like this, you need to both figure out how your zone time converts to GMT, and then you need to know if this 05 is 5 or 17 based on whether it's AM or PM. So it's kind of two things you need to do at once. It's frustrating, and realistically, whenever you measure something, you don't actually use your chronometer. You use the clock in like your Ectus or something, because it's both more accurate and easier to work with because it's automatically in GMT 24-hour time. But this is how STCW problems are laid out. So our chronometer time is 05 34:48. So 5 hours, 34 minutes, 48 seconds. And we don't know if this is AM or PM. We have to figure that out as we go. So actually, I'm going to... well, actually, no, I'll leave that. What I'll do, just to make things clearer, is I'll put ZT up here as 1036, and then I'll do ZD. So we can continue from there. So first, let's actually find our ZD, which is our zone description. It's the zone, the time zone that we're working in based off of our longitude. So we found our longitude to be 108 degrees, 20 minutes west. If we want our zone description, we can just divide 108 by 15. Comes out to 7.2. The 20 minutes would only really affect this 7.2 by like 0.1, 0.01, 0.02, meaning, well, let's just demonstrate. 20 divided by 60 plus 108. If we divide that by 15, we get 7.2 repeating, so it's still 7.2. Meaning we round this now to the whole number of 7. So we're in zone description 7. We're in the west, so that's plus 7. Before we go any further, now we've got to look at our chronometer error. So this isn't something you've seen before, but it's exactly what it sounds like. It's the error in your physical chronometer that's up on the bridge. It's how fast or slow the clock itself physically is. So we've got it listed here. Our chronometer error is 1 minute, 24 seconds slow. Write this here, 24 seconds slow. Chronometer error is going to be a lot like something else we call dip later on. Slow. Where if it says this off to the side of fast or slow or on and off for index error, that just indicates the direction. So if a clock is 24 minutes slower than what it should be, that means it's later in the day than the clock lists. What that tells you is that if the chronometer is ever slow, you want to add whatever error you have to get to the true time. And if it's ever fast, you want to subtract the error to get to the true time. So because ours is slow here, we want to add. So we're going to add the chronometer error to the chronometer time to get a closer and more accurate time based off of our, to find our true GMT. Now, how you want to break this down, because we're both dealing with our zone description and our chronometer error, is you want to tell yourself that chronometer error only refers to minutes and seconds, and zone description only refers to hours. And you don't want to overlap the two, because that's going to confuse you. Just think about this and just think about this. So if we're looking at ZT and ZD here, you could see we're in 10 hours local time with a zone description of plus 7 hours. So that would give us a GMT hour of 1700, which if you subtract 12 is 5. So that means that our chronometer time is technically PM in the afternoon. It's just 1700, not 0500, both of which could be written as 5. So that's why that's confusing. Then you come over to the minute side, and you know that you have to add your chronometer error to your chronometer time to get an accurate minutes and seconds. So you add 48 seconds to 24 seconds, you get 2, that's 3, so 72. 12, you carry the 60, becomes a 1. So 34 plus 1 is 36. So we get a true GMT time of 17, 36, and 12 seconds as the time that we actually took this shot of the sun. That's how we do it in this case. Now we're going to go on to the next problem so we can practice that again. So we're going to write out ZT, ZD, CT, CE, and GMT. T. Should probably mark that too. So in this problem, the time of our DR is 09:15. The time of our chronometer is also 05:14:27. I'm surprised that it just happens to be 5 both times. Our chronometer error is 0 minutes 53 seconds slow again. Or 00:53 slow. I'm also surprised it just happens to be slow in this case again. Now we need our ZD. So we're 121 degrees 56 minutes west. So we'll do 56 divided by 60 plus 121 divided by 15, 8.1. So our zone description is 8. We're in the west. So it is plus 8. Now we want to break it down again to just work with the hours and then with the seconds. So 9 plus 8 is 17. These are 2 different questions. I don't understand how it just happened to become 17 in both cases. And then the minutes, we add 0. Oh, but these 2 we're going to have to add together. So 27 plus 53 is 80. 80 minus 60 is 20. 2 carry over 1. And we get 7, 15, and 20 seconds, GMT. And coincidentally, very close to this one. Hopefully this next one is not that. Now we go to our next problem. ZT, ZD, CT, CE, GMT. Okay. Our zone time is 08:16. Our chronometer time is 03. Wait. Yeah, 03:14:16. Our chronometer error is, man, it's slow again. 1 minute, 47 seconds slow. I wish one of these would be fast, just so you can see the difference, but you know, slow you add, fast you subtract. It's not complicated. I just would like the example to be there. All right, now our zone description. We're in 78 degrees 29 minutes east. So 29 divided by 60 is nearly 0.5 plus 78 divided by 15. We get 5.2. So we're in 5. We're in the east, so now we subtract. So we do 8 minus 5 is, this is weird. It is 0300 GMT. Actually, no, this is fine. Okay, 0300, or I don't write that there, I write that here. So we got an hour value of 0300. Now we go to the minutes and we again add. So 16 plus 47, we get 63. So we carry the 60, we get 03, 15, 16. So now our GMT value for this one is 03:16:03. That's how you just find our Greenwich Mean Time for each of our shots based off of correcting our zone description to get our GMT hours, and then applying our chronometer error either based off of fast or slow to correct our minutes and seconds to the accurate minutes and seconds.